Well, Flavio, thank you very much for inviting me. Let's see, back next. Okay. So my talk is about methodological considerations on analyzing diffusion MRI data. And I was also asked not too long ago to also have a quick 101. Oh, it seems like my talk has not been refreshed. I made some final, some quick adjustments, but I'll have to move on without giving a proper 101 on DTI. So apparently my talk was not refreshed. But anyway, so let me start then with what I would call a typical day at the office. Okay, so this is me. I'm the physicist. I'm the nerdy guy in the office, and here is rich and handsome Dr. Bob, and he steps into my office and says, "Hi, Alex. I've been collecting advanced DTI data. Can you help me with the analysis?" And obviously, if you look closely, it just means like, yeah, you do it for me. Okay, so I'm already kind of excited, advanced DTI data. So I'm start dreaming like high quality, human connectome project-like data. But in practice, I'm very disappointed. Okay, so this is where he kind of shows off with like, look at these nice colorful images. And he's even bragging like, I collected 300 of them. Okay, so I'm kind of weary. How do you say this diplomatically? I hope you've got a big garbage bin. The thing is, what people tend to neglect is that if you look at an entire pipeline of acquiring your data, choosing some model, using some analysis approach to get your statistical inferences, is that this step is typically neglected. Okay, so what you should do is always do a proper QA, quality assurance, quality assessment. Okay, and here's a kind of motivation why. If I asked 18 different centers across the world to send me their typical data set. And you know what that means, right? Typical data set. It's like their one-off Rolls-Royce quality data set, and they're very proud of it. But if you look at this one, for instance, I mean, is that even human? Okay, so there's a very wide diversity in image quality, and this is kind of historically, I think people have been looking at these images and think like, oh, nice colors, must be right. Okay, so let's have a quick look at some of these data sets in more detail. So what about this one? So in this case, you can probably appreciate that the gene looks a bit fuzzy, and there's this blue patch below it. So what went wrong here? Well, in this case, the subject was not informed to lie still in the scanner. That is obviously problematic with MRI. So one thing that you should do, obviously, is before you start analyzing your data like this, is just look at your data, and you can do this really quickly, right? I'm looking here at roughly 3,000 images within 10 seconds, right? And looking at it at a high frame rate in a matrix like this, but you can immediately spot gross artifacts, right? But here's a more subtle one, okay? And here I kind of advise you to look at your data from different viewpoints. And by that I mean if you acquire your data axially, then also look at your data from a sagittal or a coronal point of view, because you'll spot artifacts. And obviously we all spotted this artifact, but did you notice this hyper-intense band over here? Well, you will never spot this on an axial image, because if you cycle through all the axial slices, your brain, dynamically adjusts, the intensity range, and you will not spot it. And again, this was an artifact not noticed, and, this is systematic, so that's problematic. Okay. So let's have a look at another one. This was kind of interesting. So let me zoom in again. So what was the problem here? You might not notice it, but remember the color encoding convention, typical with DTI? So here you can appreciate that, the pyramidal tracts are in green, but green is typically front to back, and, blue is up down. So here they've been interchanged. Is that wrong? Well, not necessarily. Okay, that's just a convention. So this is, the proper convention, but the more problematic issue is that if there's an axis mismatch, and by that I mean if I flip along a specific axis, let's say, the top-down axis, you'll get something like this. So the color encoding will remain the same, in this case, the correct version, but obviously you can appreciate that this would be problematic for tractography. And after the break, Maxime Descoteaux will talk more about tractography, but the point I want to make is that you sometimes get, colleagues that are very enthusiastic, showing an image like this, like, look at this patient, you know, no cingulum bundles. And I'm like, okay, there was an axis flip. You know, just if you do it properly, you get something what you would expect. Okay, and this is something that you will hopefully not encounter under Scanner Console software because it's CE or FDA approved, but with, you know, offline packages, things like these can happen. Okay. Something that we've been working on more recently, physically implausible signals. I must admit that the acronym should have been chosen more diplomatically, PIS. But it's nice to remember because we don't want PIS in our data. Okay, we don't want something which is physically implausible. So let me show you the diffusion equation, and you know this is the only equation that I'm going to show. But you know, as any self-respected physicist, I should show at least one slide with an equation. So what we're showing here is the diffusion attenuation over here, right? So this factor is always smaller than 1. So that means that our diffusion-weighted signal is always smaller than the non-diffusion-weighted signal. We always look at attenuation due to diffusion. I mean, this is what we expect, right? Well, in practice, we often see the opposite. So that's really physically implausible, right? So let's have a quick look at an example data set, okay? So here we're looking at the splenium, and you might not notice anything abnormal, but if I just overlay, and now on the FA map, all the areas where we do find a diffusion-weighted signal which is larger than the non-diffusion-weighted signal, you know, you would be amazed how many voxels actually are flagged like this. Okay, so this is called a PIS map, you know, reflecting all the areas with dodgy signals, basically. So you may wonder, like, okay, well, why is this the case? So let's have a quick look in more detail about these, you know, 4 voxels over here. And if you look at the non-diffusion weighted image, you can appreciate that in this area, the signal is really low, right? So you've got this really bright signal over here from the CSF, and then a darker signal in the white matter. But at the interface, you see this, you know, tremendous drop. Why? Well, the artifact that you know, is actually described, bears this, you know, this guy's name, and this guy was actually, you know, called by Einstein the most smartest, you know, the smartest person he ever met. So if Einstein says something like that, he must be really, really smart. Anybody, any idea? Mr. Gibbs. Okay. And this is an artifact which is actually quite common, and not just in diffusion MRI, but in the entire arena of MRI, right? So what that basically means is that if you've got if you haven't got a sufficient amount of high frequency content captured with your MR system, then if you're doing the inverse Fourier transform, you will see these kind of undershoots and overshoots at the interface. So here's your, let's say, CSF signal over here, and then there's white matter signal over here. So at this interface, you see these kind of ripple effects. So now if we look back at the some of these images, it's actually quite interesting, and I'm not sure if it's, you know, properly seen over here, but there is some, you know, clear rippling going on. And if you then go back, you can actually see that, well, in these areas where you've got, you know, PIS in your data, there are some, you know, abnormally high FA values. And this is something you can appreciate when looking back, you know, at these color-encoded FA maps, for instance. Okay, so here's another example. This is a patient with a lot of atrophy. So there's, you know, a lot of CSF. So this ripple effect is really dominant in this area. So again, you see all these regions interfacing between white matter and CSF, where you see all these, you know, regions of PIS. And well, I don't think I've ever said PIS that many times, but so what we basically want to do is then get rid of this PIS. Okay, so how do we do this? Okay, we can use an off-the-shelf total variation approach, and there are many other approaches nowadays. But I'll just show you before and after. So this is before correcting for Gibbs ringing artifacts. This is after. Let me just quickly toggle between them so you can appreciate, you know, the fine differences. Also notice that the edge information is kind of maintained. So we're not smoothing away the artifact, and by doing so also, you know, smearing out or edges. Okay, so our effective resolution is kind of maintained. Okay, moving on to the next one. So what happened here? Okay, so again, to the novice in this field, you may wonder, well, just nice colors. But if you're more familiar with these images, you may notice this kind of red blob. Okay, so what does it mean again? Red means color encoded left-right. Bright means high coherence of the underlying tissue, so high anisotropic diffusion. So this kind of suggests that there is a direct connection between the occipital poles. I don't think so. Okay, so it must be an artifact. But how can we be sure that it's an artifact? Well, one approach that is very convenient to look at artifacts is by looking at the residuals from your model estimation. Okay, what do I mean by that? Well, if you assume a set of points, then the residuals are basically the difference between what you measure and what you estimate. Okay, so the little white lines, these are basically our residuals. So if there's a point far away from the red line, that means that that data point was not well supported by the underlying model. And we can do exactly the same with our diffusion equation. There are also models, let's say the diffusion tensor model, so we can also compute residuals there. And ideally, you want to have a map which looks like this for the residuals. Nicely uniformly distributed and ideally low values, meaning your data matches your model properly. So you may wonder, well, I don't think this is really good quality data. Admittedly, it may look a bit noisy, but at least there's no artifacts in there, like systematic artifacts. So let's have a look at this one again. Okay, so here we see the color-encoded FA map. Difficult to judge what is an artifact, what is not, if you haven't got prior knowledge. But with this residual map, you can clearly see this kind of light bulb effect appearing. Aha, here is something fishy going on. Okay, and in this case, it was the infamous vibration artifact, and I can highly recommend reading this paper by the Oxford group. So if you do have an artifact like that, and there are some vendors that are more prone to this artifact than other ones, I'll be very diplomatic, not state any names. Come talk to me afterwards. But you can apparently get rid of this artifact by including this, this approach here. Here's another one, and I really like this one because if I ask even the diffusion experts what is the artifact, they cannot state what it is. They cannot see it. So this is, again, the power of this residual map, and in this case it was insufficient fat suppression. So you can see this kind of band artifact. And maybe retrospectively you could say, like, well, I see something dark over here, but it's kind of self-fulfilling prophecy here. Okay. Here's another one. In this case, I'm actually showing you already the residual map. So what's the artifact here? Well, in this case, there is no artifact. So you may wonder, like, well, but this is clearly structured residuals, right? Well, in this case, the data set was acquired with a b-value, which was 3,000. So a lot higher than what you would usually use with DTI. So in this case, our diffusion is not, assumed Gaussian anymore. In this case, we're not looking at hindered diffusion. We're looking at restricted diffusion. And that means it's non-Gaussian. Well, if it's non-Gaussian, and our model, the diffusion tensor assumes Gaussianity, then obviously our model is not appropriate. Okay, so the nice thing about these residual maps is that, how do you call this? There's two sides to the coin, right? On the one hand, it says something about how well does my data fit the model in terms of data quality. But on the other hand, if the model is wrong, you'll also see high residuals. Okay, so the analogy would be something like this. This is a good model for this set of points. This is a bad model. So okay, we're not going to model this set of points with a sinusoid. So here our residuals would be high as well. Okay, so why the structure? Well, in some areas you have got crossing fibers which are really dominant compared to other regions. So that's why you saw the structure. A final example. Where's the artifact? Well, I'll actually help you guys. Okay, where's the artifact? I'll even zoom in. Okay, interestingly, this is not an artifact. So while you may think this is an artifact, right, because we're looking smack in the middle of the corpus callosum, which should be left, right, oriented in red, but then you see this kind of green patch in there. Green means front to back. Well, in this case, the residual map didn't show anything. It was nicely uniform, no artifact. Well, it's kind of cool. This is basically Russ Poldrack's brain. So I think it's probably at the conference as well. Well, very smart professor in Stanford. We all know he's got a beautiful brain, but we didn't know it was that special, right? So in this case, nobody noticed until they looked at their diffusion data. So if you look at the T1 data set, nothing abnormal can be spotted. And this is one of the beauties, one of the power, key things that diffusion can provide you. Within the white matter, you can be more specific in terms of the architectural configuration of the pathways. And this is even with what we would call nowadays a simplistic model of the diffusion process, the diffusion tensor. But even this simple color encoding already provides you more information that you could ever achieve with, a T1 weighted image. Okay? So this is part on the quality assessment, very important. Okay, now I'm going to describe a few of the kind of processing steps that we need to do. First one is I think, arguably the first one you need to do. So you acquire data, and then you need to check how basically how stable your signal is. And you can do this easily if you have data acquired with your B0s kind of interleaved, at every sixth volume you acquire a non-diffusion weighted image, for instance, then you may notice that the signal itself of these non-diffusion weighted images may not be stable. So ideally, you would expect if you acquire a non-diffusion weighted image again and again and again, it would be the same, right? But what you notice is due to scanner instabilities, system heating up, that the signal to noise is changing, or the signal itself is changing. Okay, so in this case, you can clearly see that, this is a real data set, by the way, so you can see that the signal is really changing. Okay, and it's not just the non-diffusion weighted image, obviously, it's also all the diffusion weighted images. Okay, it's a little more subtle, obviously, because you're looking at lower signals in general, but the same trend is still, visible. The nice thing about this is that you can correct for this, in a trivial way. You basically model this trend. You can use a low-order polynomial, and then use this trend to correct for the signal, and then you end up with something with what you expect, right, to be more stable. And just to show you what the effect can be on a color-encoded FA map. So this is before correction. This is after. I'm going to quickly flick. I'm not sure if you can see it, but there's a difference. Okay. And just to drive home this point, let me just take the absolute FA difference here and plot that. And again, you may wonder, well, it's 0.04, maximally, but that's the absolute value. If I take a percentage, right, so divide by, the FA itself, then you can clearly see that, the majority of all these voxels have differences, more than 1 to 2%, which is typically kind of the effect of interest that you see in, clinical applications or neuroscientific applications. Okay. Second one is correcting for subject motion. So here's our subject again, not informed to lie still in the scanner, and this is the end result. But luckily we can correct for that, and you'll get something like this. So here you can nicely see that, at each location in a data set, we've got the same anatomical structure across all the diffusion-weighted volumes. One thing that is typically neglected at this stage is that, in this case, our contrast is orientation dependent. Okay, so with fMRI, this step would be sufficient, right? You just use the registration, the warping, and then you're done. In this case, our data set contains information. So this is kind of a dummy schematic here. So here's our subject without subject motion. Let's assume our subject moved at some diffusion-weighted volume. Well, if you were to naively reorient your data set with registration, then you'll get something like this. Okay, so our contrast itself also contains orientation information. So what you should do then is also correct for the B matrix. You need to reorient the information that is captured, within the gradients. So here's an example. This is our subject just lying still, and then there you go. You acquire a diffusion-weighted image. Now let's assume our subject moved a bit. Okay, so here you go, extreme case. And then you acquire your data. So notice it's the same diffusion gradient orientation. If you were to just reorient it, so correct for subject motion, then you can appreciate that the contrast is different, right? So if you then estimate your diffusion properties, then you will notice some kind of dodgy, signals if you haven't corrected for the B matrix. So in a nutshell, if you reorient your data, for subject motion, then also just reorient or rotate your B matrix. And simultaneously, we tend to correct for the eddy currents. That was also mentioned by the previous speaker. So by the, the fast switching of the gradients, your data basically gets deformed, like stretches and skews. And if you don't correct for that, well, you can clearly see these bright rims appear. Okay, so it's kind of a telltale sign that something was wrong, or that you didn't correct for it properly. If you do correct for it properly, you'll get something like this. And again, this can be done with registration-based approaches. Okay, so before and after correction. A very notorious artifact are called, the EPI deformations, susceptibility-induced deformations. In this case, if I just rigidly align our diffusion data to, let's say, a T1 dataset, which I assume is not corrupted with deformations, then you can appreciate that, while the back of the brain is nicely matched, the front of the brain, there's clearly a shift, right? So it's highly nonlinear. You cannot correct for this misalignment with a global affine transformation. You need something more advanced for that. And I'm just going to show you a few examples before and after correction. So this is before correction, and in this case the diffusion data was a bit compressed, and this is after correction. Okay, so you can appreciate the improvement. It's not perfect yet, but at least it's better than not correcting for it. And then people say, like, well, this is an area very well known for this artifact, orbitofrontal cortex or frontal cortex. But higher up in the cortex, I don't have that issue. And that's why they motivated that they don't correct for it. But let's go higher up in the cortex. And indeed, you may argue, well, my alignment is pretty good. But again, after, before, after, before. And you can clearly see the improvement, also the nonlinearity. And especially if you're thinking of, let's say, connectomics kind of analysis later on, then you need to have a proper match between your white matter, or in general your T1, and your diffusion data. I guess one of the tricks to make this work properly is to constrain the degrees of freedom of your warping. And in this case, we've got prior knowledge. Typically, our phase encoding is along the front-to-back orientation. So it's in that orientation that we see these kind of distortions. So if you correct for it, we can constrain the front-to-back orientation as the only degrees of freedom that we need to change. So if I now show it, corrected, uncorrected, you can appreciate that it's only, front-to-back distortions that are now being corrected. So if you focus on the genu in the brainstem area, you can clearly see the improvement. Interestingly, if you have acquired your data, with different polarities of the phase encoding, so front to back or back to front, you may still find differences if you do the analysis. Okay, so if you have acquired them in both, polarities, then I would suggest to use this eddy tool. I was also mentioned by the previous speaker. That basically corrects simultaneously also for the eddy currents and EPI deformations. And finally, the diffusion estimation approaches. This is kind of trivial, but it's kind of neglected often, is that obviously if you've got a set of points which are nice in a way, nicely distributed, then this fit is okay. You just use an ordinary linearly square and you're fine. But if you've got an artifact, like a signal dropout, well, if you then estimate your line, it will be biased towards this outlier. Any statistician will agree, this is trivial. What you should do is use the robust estimator, meaning identify the outlier, get rid of it, and estimate your model to the remaining data points. Okay. One of the big challenges here was that, well, it takes forever to compute. Okay, so more recently, Chantal Tax has done a lot of work on improving the estimation speed, so now it only takes a minute or two to actually compute this for an entire data set. And here's an example. So this is what the scanner console would give you. So this is a child with a lesion moving a lot. It's kind of a worst-case scenario. I kind of cherry-picked the axial slice over here, obviously, but if I show you the corrected version after robust estimation, you can still appreciate the improvement overall also on the coronal and the sagittal slices. Okay, there are many approaches to analyze diffusion data, and this is kind of our bless, but at the same time, it's really annoying. Which one should we choose? There's many flavors, and they all have their advantages and disadvantages. And I'll just touch upon a few. One of which is tractography. This is kind of a disclaimer I typically make. What we're doing with tractography, and again, Max will talk about this a lot more in detail, is that we're looking at an indirect way of reconstructing, fiber tracts. Okay, so these are not tracts; these are, reconstructed pathways, assuming some diffusion profile. This is something completely different, and we're also bound to many artifacts. So typically, we show an image like this. But there's noise in the data. So in a way, if you want to capture your uncertainty, then it would be more relevant to actually look at an image like this, where the uncertainty is associated at each point along the pathway. But this is obviously not convenient to look at. People get, dizzy by just looking at it. But this is just to kind of give you a kind of awareness that our data is not perfect. Another thing that is very important to be aware of is the partial volume effect. And here I just want to show you a schematic of a tract, that if we have a bigger tract over here compared to the smaller tract, that this tract will be less affected by partial volume voxels, which are typically at the interface between this tract and other tissue, right? So if you've got a bigger tract, your partial volume effect will be smaller if you're estimating some properties from the entire tract. Okay, so we put this to the test. We looked at several subjects. We used our virtual scissors, cut it in half, looked at the top, and here you can already see the partial volume effect, right? So in the middle, you've got high FA values, and at the edge, there's lower FA values because you're interfacing with CSF or gray matter areas, right? So by that rationale, if we've got bigger tracts, meaning, bigger diameter of tracts, then we would assume that the FA would be larger because at the edge, the FA is lower. So if you've got a bigger tract, the higher FA voxels in the middle will put a larger weight to the total estimate. Okay, so if people say the FA of this tract is 0.6, well, it may be modulated with volume. Okay, so this is what we investigated, and to our amazement, the vast majority of the variance in FA could be explained purely based on size. Okay, so luckily there have been some follow-up studies that also used volume as a kind of covariate not of interest, where they could still see an effect of FA on, let's say, developmental, studies. Okay, because it's important to be aware that if you're making a claim like, my FA in this group is larger than in this group, you don't want it to be modulated by something like volume, okay, which is probably not of interest. Another issue is the model that we choose, and Flavio will talk about that in the next talk as well. But very briefly, with DTI we assume, like I mentioned before, a Gaussian diffusion profile where our pathways are unidirectional at the voxel level, but in practice, our voxels contain many pathways interdigitating, etc. I typically like to show this kind of polarized light imaging microscopy images, just to kind of bring us down to earth on how complex the brain is. So this is part of the medulla oblongata, so an axial slice. And this is our voxel size with diffusion MRI. Okay? So when people say, we'll wait a year. When all our voxels, get smaller, we'll get rid of this, crossing fiber issue. Well, I don't think so. I mean, even axons branch, right? So, and that's looking at the micrometer level. So we're not going to get there pretty soon. So what can we do about it? There's many models that can be used. So if you look at the centrum semiovale, where we know there's many kind of fiber bundles interdigitating, you'll get something like this with DTI. And this is, with spherical deconvolution approaches. Obviously, this will also affect tractography. So if you look at this kind of mid-coronal section and you're looking at some part of the corpus callosum, if you use the same seed points, but then a different model, you may end up with something like this, okay? And this is typically the areas, where these crossing fibers exist, and with DTI you cannot retrieve them, okay? Another approach, I guess most of you are familiar with this one, TBSS. Can I see some hands who doesn't know this approach? 4 people, that's what I guessed. Great. So it's by far, the most popular approach to analyze data, diffusion data on a voxel-based level. So how it basically works is, you've got your set of subjects over here and some patients over here, for instance, if you're doing a group analysis. And then basically you press the right button and you get your result. Okay? So obviously I'm kidding, but this is basically why it's kind of popular as well. You just feed in FA maps, and you'll get your result as if where in the brain do I find the difference between 2 groups. Well, how it does work is obviously, and I'll be very quick about this, is that you first create a kind of a common template, or you use the one that is provided by the FSL tools. And then you can compute a skeleton of this mean FA map, which you then back project to each subject to find the locally maximal FA value, perpendicular to the sheet, because the skeleton in 3D is a sheet. And then you basically got all your values on the skeleton, from which you can then do your statistical inferences. Well, as with any techniques, I've shown tractography is far from perfect. The same holds also for, TBSS. So I'm risking my career here. But anyway, I will kind of show you some methodological considerations on TBSS. I'll be diplomatic. First of all, tract-based, at some point, you'll notice in the paper, they're talking about a tract skeleton. This is kind of confusing because what it should be is an FA skeleton, right? That's what they're computing. There's nothing really, tract related. They're not using orientation information or a tract itself. So, you can compute a tract skeleton. So here I've just computed a tract. And you can compute a skeleton in red. And if you overlay it with the FA skeleton, it's similar, but it's not the same. Okay, but I think the main issue here is that it causes some confusion, that people think that you're looking at tracts, but you're actually looking at FA values. And secondly, I think more, profoundly problematic is that the skeleton itself may be biased with respect to the effect of interest. Okay, so this is kind of controversial, but let me try to explain this. If you look at the color-encoded FA map of that single subject, which was already aligned with the skeleton, and again, it shouldn't be perfect, as you can see, which is fine, because in the next step, what happens is that from the skeleton, you project to find the locally maximal FA value as indicated here, right? And then you do this for every subject. But what if your subject or your effect of interest is a pathology or something is changing, right? Let's assume we're looking at a pathology and the FA is changing. The FA is typically lowering. So you could simulate it something like this. So what happens now is obviously if you do the skeletonization, the projection step, then it may actually terminate prematurely and find another FA value which is not related to the effect of interest because the FA is not locally maximal anymore. Okay? So this is something to be aware of, that sometimes the pathology itself may induce an effect that causes the projection step to be malfunctioning, basically. Okay? A third one is related to, to interpretation, basically. If I ask you, what is this? Okay? Is this part of the skeleton? Is it part of the corpus callosum, or is it part of the corticospinal tract? Well, both or none. It's difficult to say what it is. And this is because if you've got different structures interfacing with each other, converging towards each other, then on the FA map alone, you cannot really disambiguate, to which structure it actually, holds. So the skeleton there basically collapses the two different structures on top of each other. So for some subjects, the FA may actually be projected from the corpus callosum, but from other subjects, it may be the corticospinal tract. And there may be other, there are many other structures that I can think of that have a similar issue. Like if you look at the orbitifrontal part of the uncinate fasciculus, it is also interfacing with the fronto-occipital fibers, right? So also at that area, you kind of see this collapse of multiple structures on the skeleton. So here you could argue that the specificity of a finding may be, compromised here. So I guess the multi-million-dollar question is, if TBSS is not really tract-based, why the acronym? Well, who was the last author of this paper? Tim Behrens, right? Who was the first author of this paper? Steve Smith. Timothy Behrens, Steve Smith. Is it sinking? TBSS. Okay. They do have a sense of humor, right? Okay, and then finally, a quick word on this guy over here, this kind of blobs over here. Well, this is called connectomics, and I guess we're all familiar with this approach. Very fashionable. It actually exists more than a decade now, I think. And the key concept here, quite rightly so, is that obviously we should look at the brain not from regions, we should look at it from an integrated point of view. We've got many areas working together, and we should look at this from a network point of view. And I'll be very brief on how this works. Basically, you define some nodes, as they're called, some brain regions, and from which you can then say, like, okay, what are the connections between these regions? So step 2 is to define what we call the edges, and then you find all the combinations between all these regions of interest. And then finally, you end up with what we call a connectivity matrix, which captures all the information that you want. So every combination of arrow-wise where we find tracks, you can basically put in a number. And this is basically also one of the challenges, is that what number do we put in? So there's many challenges. I will not go into detail here, but there's a very, very nice special issue over here that I can highly recommend reading. It's the Connectomics special issue in 2013 that already states many areas that we need to work on. One thing I can say for sure is that interpretation becomes even more complex. Remember all the issues that we have. Well, put an additional layer on top of this, and you'll get basically something which looks like this. And some of my peers say that and they think that the artistic value is higher than the scientific one. Okay, so this is still kind of debatable. If you want to get more depressed, here's another 25 pitfalls in analyzing diffusion data. So I can highly recommend this paper. And I would like to conclude by acknowledging my collaborators, and in particular, the members of my team. They're doing all the hard work. And I would like to thank you for your attention. Thanks.